We live in a world of nuances, where things are rarely completely black or white. However, for decades we have tried to make computers understand our world using only binary logic. 1 or 0, yes or no, true or false. But what about all the shades of grey in between that make up most of our human experience? For over 2,000 years, Aristotelian logic dominated our thinking. But in 1965, a professor at the University of Berkeley named Lotfi Zadeh proposed a radical idea. What if, instead of thinking in absolutes, we accepted that things can be partially true and partially false at the same time? This simple but profound idea would give rise to fuzzy logic. We will not only understand what fuzzy logic is, but how it connects to our natural way of thinking, why it is crucial for the future of artificial intelligence, and how we can apply it in real-world situations. We will start with the fundamentals of common sense, delve into the mathematical theory, and culminate with practical examples that demonstrate its transformative power. Common sense is not a single skill, but rather an integrated set of abilities that allow us to navigate the world. Let's break down each of these 5 fundamental pillars. Contextualization is our ability to adjust meaning according to circumstances. What is hot in winter is not the same as hot in summer. What is far on foot is not the same as far by car. This contextual flexibility is fundamental to common sense, but extremely difficult to program into machines. Every experience we have is stored in our internal database, not as raw data, but as learned patterns. When we encounter a new situation, we automatically consult this database and find the most similar pattern. This process of pattern recognition is instantaneous and largely unconscious. Sociologist Juan Soto Ramirez reminds us that common sense is deeply shaped by culture. What is obvious in one society may be completely illogical in another. This cultural knowledge acts as the operating system that gives meaning to our social interactions. Heuristics are mental shortcuts that allow us to make quick decisions with incomplete information. Although they sometimes lead us to errors, in most everyday situations, they are incredibly efficient. The true mark of common sense is flexibility, the ability to adjust our rules when circumstances change. This adaptability is what allows us to face novel situations without having to completely reprogram ourselves. The fundamental difference lies in the characteristic function. While crisp sets use a step function, all or nothing, fuzzy sets use continuous functions that allow for intermediate degrees of membership. Mathematically, a fuzzy set is simply an assignment of membership degrees to each element of the universe of discourse. This simple extension of classical set theory opens up enormous possibilities. Basic operations are naturally generalized from classical logic. However, the richness of fuzzy logic allows different operators to be used depending on the context through T-norms and T-connorms. The choice of the appropriate operator depends on the application. In industrial control, the minimum and maximum are often used, while in complex expert systems, smoother operators such as the algebraic product may be preferred. Linguistic variables allow us to work with natural language concepts in a formal way. This 5-component structure captures all the aspects necessary to represent our linguistic knowledge about a variable. Modifiers allow us to adjust the meaning of linguistic terms in a systematic way. This is crucial for capturing the expressive richness of natural language. Mamdani's method is intuitive because it maintains the linguistic nature of both the antecedent and the consequent. However, the defuzzification step can be computationally expensive. Takagi, Sugeno, and Kang propose this model where the consequent is a mathematical function rather than a fuzzy set. This eliminates the need for defuzzification and makes the system much more efficient. TSK systems with singletons are extremely popular in industrial applications because they combine computational efficiency with simple implementation. Each rule suggests a specific value, and the final output is a weighted average of these suggestions. When we analyze how we think, we discover that our natural cognitive processes correspond almost perfectly to fuzzy logic operations. It's not that fuzzy logic mimics human thinking, but rather that both solve the same problem: how to handle uncertainty and vagueness in a complex world. The combination of fuzzy logic and common sense gives us the best of both worlds: the precision and scalability of computers, along with the flexibility and contextualization of human thinking. The future is leading us towards increasingly integrated systems, where fuzzy logic will act as the brain that gives artificial intelligence common sense, while machine learning provides the ability to learn and adapt. In the end, the real revolution is not in creating machines that think like humans, but in creating systems that complement and amplify our intelligence. Fuzzy logic reminds us that technological excellence does not have to mean a loss of humanity. On the contrary, by accepting and formalizing uncertainty, vagueness, and context, we are creating technology that honors the complexity and richness of human thought. As Lotfi Zada said, as complexity increases, precise statements lose meaning and meaningful statements lose precision. In an increasingly complex world, we need systems that understand this profound truth. Fuzzy logic and common sense, together, show us the way to artificial intelligence that is not only powerful, but also wise, contextual, and in the best sense of the word, human.